Good morning, and wish you all a happy holiday today. And that's the reason why I kept this class in the morning. Good morning, my dear warriors. Welcome to the NCERT line by line series, and we are already on chapter number 5. Can you believe it? Those students probably who thought that, sir, am I late in my preparation? Sir, can I do it? You should feel very proud and extremely, I would say hopeful, because by this time, had you not started your NCERT line by line series, you would not have done these last 4 chapters. And today we are on to the 5th chapter and slowly 6th, 7th, and we'll be done with the complete NCERT very soon. So guys, need your massive support, need your massive love, and not just in terms of hitting that like button, but also subscribing to the channel, talking about this channel to all your friends. So let's start with magnetism and matter with your captain Shreyas. Hi Krishna, hi Sumi, hi Sukanya, hi Srivali. Good morning Marday, and all the warrior Pandus have assembled. Hello Sumati, hello Chitra and Saurabh. Welcome warrior Pandus. Hi Krishna, I'm very good. Hi Janlisa, I'm doing very well Sumi. Thank you so much. And all those of you who are new to the channel, meet your new friends, meet your buddies who are going to be the future doctors with you. And this channel stands for all the students who want to sincerely prepare for the NEET examination. Okay, so let's begin with the class. And if you have missed any of the classes, remember all the lectures are just available just one touch away in the description box, completely free of cost. You can see it right over here. Yes, get complete NEET preparation treasure box. So just click on this link. If you do not have a Vedantu account, create it. It's free of cost, right? And you will see all the lectures with the notes, PYQ test, chapter wise PDF, as well as NCERT solutions, 10-year PYQs. All these things are arranged line by line. Yes, over here in your treasure box. The link is there in the description box. Do not forget to check it out. All right. So I hope you have marked your attendance. Let's begin. Yes. So reading NCERT with me. Thank you so much. Hi Ashwarya. Hi Disha. Good morning. Let's begin. Now in this chapter, basically we talk about, permanent magnets, usually like a bar magnet, north-south pole, horseshoe magnet, and how do these properties come, and the different types of properties of materials related to magnetism. That is what you study. Just one sec. So that is what you're going to study in this chapter. So here they say magnetic phenomena are universal in nature. That means it is there everywhere. There are distant galaxies, invisible atoms, human beings. Everything has some kind of magnetic property associated with it. In fact, the earth itself is magnetic in nature. And we know this, that so many birds and animals navigate their migrational patterns via the earth's magnetic field. And for centuries now, old navigators have been finding and exploring different areas during the earth's magnetic field. So this word was derived from an island in Greece called as Magnesia, where that magnetic ore deposits were found as early as 600 BC, that's 600 years before Christ. That is what, this ore was found in Greece, and they found that it attracts other things, and that island name was Magnesia, and that's how that name came. Don't worry, this won't be asked in NCERT. That's why in your NEET exam, that's why I'm not underlining it. So in the previous chapter, we have learned that when you move charges or you pass a current, magnetic fields are produced. We remember this. You take a wire which carries current, immediately it behaves like an electromagnet, right? We have seen this. Also, this was made by Ørsted just very lately in the 19th century, and Biot-Savart's law and Ampere's law tells me how to find this magnetic field. Ørsted was that guy who discovered this phenomena. Biot-Savart's and Ampere's law tells me the magnitude of the magnetic field calculations for any kind of geometry. Now in the present chapter, what do we what do we see? So some of the commonly known ideas regarding magnetism are: the earth behaves as a magnet with the magnetic field pointing approximately from the geographical south to the north. Now this is the first thing. Okay, let me just underline. Earth behaves like a magnet with the magnetic field pointing approximately from the geographical south to the north. What do I mean by that? I will come to it. When a freely suspended bar magnet is left, it points in the north-south direction. The tip which points to the geographic north is called north pole. The tip which points to the geographic south is called as the south pole. So again, a bar magnet which is freely suspended points in the north-south direction. The tip of the bar magnet which points towards the geographical north is called as the north pole, and the other way around is called as the south pole. Okay, now let me explain this. Let me get the earth for you. So you might have heard about some, Pandu Champas saying, I will bring the moon for you. So your captain Shreyas Sir brings the earth for you. Yes, I can't get the moon for you. That is for Pandu and Champa. I'll get the earth for you. So in this earth, we know earth spins around like this, and this is where we are, somewhere over here. This is India. I hope you can see that on your screen. Anyways, that's not the point. This is the North Pole. This is where your Europe, North America, Canada, Alaska, Russia, somewhere and all, it's here. So this is your Arctic region. So here you have the North Pole. If you go down below over here, lot of oceans, somewhere below Australia, somewhere below Argentina, right? Some people support Argentina team in football. So somewhere here you have Antarctica, and somewhere down here you have the South Pole. This is South Pole, this is North Pole. Now as per this, the earth behaves like a magnet with the field pointing approximately from the geographical south. This is the south and this is the geographical north. So the magnetic fields go from south to north. So what do I mean by that? Let me explain. Okay. So see guys, very simply put, let me put it on the next slide. That will be better. If this is our earth, okay, this is our south pole, but this is also called as the geographic south. This is called as geographic north. And the earth behaves like a magnet from south to north, meaning you can imagine earth to be a magnet like this, where the earth's magnetic north pole is actually over here and the magnetic south pole is over here. This is very, very important. The north pole is here, the south pole is here. Now because of this, what happens is, by the way, let me put it over here. This is your magnetic. This is the magnetic north. And this is your magnetic south. Very, very important. Because of this, what happens is, this was your geographic south, this was your geographic north. The magnetic field lines from the earth, they will travel something like this. This is how they will travel. Obviously, they continue inside, but I have not shown it. They will continue inside as well. But you get the idea. It goes somewhat like this. It goes somewhat like this. There will be many more field lines. They will be going like this too. So these are basically your magnetic field lines around the earth. They go around like this. This is how they go around. There will be even more field lines like this. So can you see near the surface? Imagine there is some Pandu. Imagine there is some Pandu over here. He's standing on the earth. This is the Pandu somewhere here. What does he see the magnetic field lines doing? What does he see the magnetic field lines going? The magnetic field lines are going from the south to the north pole geographically. From the south to the north pole geographically, but actually what is happening is at the south pole you have the north of the magnet, and that north is emitting the magnetic field lines and it is terminating at south pole, but it continues inside, we know that. Is this point very clear? Is this point very clear? How the magnetic field lines are going from south to north. That is what they have mentioned, the magnet with the magnetic field going from south to the north. With the magnetic field going from the south to the north. So whenever we say south, do we say geographic south or magnetic south? So whenever they say south, anybody says south, it is understood it is geographical south. We do not talk in magnetic terms. We know at the back of our mind, at the south pole, Earth's magnetic north pole is present. Okay, that is one thing. Next important thing which you should also know is that if Pandu was holding a compass, then what will that compass do? Now we know the behavior of a compass exactly. So let's say for example, so this is a magnetic needle, let's say. Now, if the magnetic field is somewhat like this, then what will happen is there will be a torque on this particular magnet, and that torque we have already seen. It is basically magnetic moment cross magnetic field. It will try to align the magnet. It will try to align the magnet in equilibrium along the field, along the magnetic field. This is what happens. So remember, there will be a north pole over here, there will be a south pole here. So definitely there is a magnetic moment which experiences a torque, because of which it tries to align itself. So eventually, if the magnet has aligned in the direction of the magnetic field, so if somebody brings in a magnet or a magnetic needle, they will see that the magnetic needle will behave something like this. Observe this carefully now. This is our magnetic needle. This is how it will behave, where this is the north pole, this is the south pole. This is the north pole, this is the south pole. This is north. Generally, the north is shaded in a magnet to make it recognizable that it is the north pole. So the north pole will align in the direction of magnetic field, because that's how the magnetic moment will be. So the magnetic moment will be in equilibrium with the Earth's magnetic field, Does that make sense? So can I say that the part of the magnet which points to the geographic north is called the north pole, but actually what is happening is the north pole is getting attracted by the magnetic south, and the south of this needle is getting attracted by the magnetic north. So that's why the south is attracted by this north, but it feels as if the south is attracted by the south pole of the earth. Don't think like that. We know north and north should repel, north and south should attract. So some people think, sir, how, sir, the earth's north pole is there, and how the earth's how the magnetic needle's north gets attracted by the earth's north? No, actually at the north of the earth you have the magnetic south. So this needle's north gets attracted to this guy. Keep that in mind. Is this absolutely clear now? Everyone, thank you Madhumati for that compass, and Krishna too. Yes, very clear, Vetri. So glad. Very good, Inshu. Okay, so that is what exactly happens. If I put a needle, it will align. The north will be closer to the south of the earth, which is the geographical north. That is what exactly they have mentioned right over here. The bar magnet is freely suspended, it points in the north-south direction, and the geographical north is where the tip points of the magnetic needle. The next important point which they talk about is over here. There is a repulsive force between north poles, and yes, there is an attractive force between the north pole of one magnet and the south pole. Makes sense. So there is a repulsion pole, a repulsive force between the two north poles or the south poles. Basically, when poles are alike, they repel, and there is attractive force between north pole and the south pole. Basically, opposite poles attract. We know this as a matter of fact. So, north and north versus north and south. Here, the force will be repulsive. Here, the force will be attractive. We cannot isolate north or south pole of a magnet. If a bar magnet is broken, then we get two similar magnets with somewhat weaker properties, unlike charges, which can be isolated as positive, negative. Magnetic monopoles do not exist. We can't isolate north or the south pole of a magnet, and magnetic monopoles do not exist. What does it mean by this? If you take a magnet and you break it down into smaller parts, and this magnet lets you break it down into more smaller parts, no matter what you do, you will always find it will have the north pole and the south pole. North, south, north, south, north, south, north, south. You can never ever isolate it, no matter how much breaking you do. So individually you cannot separate the poles. It's like, imagine the universe made Pandu and Champa. Pandu and Champa can't be separated. No matter how much you break Pandu and Champa, even in the tiniest bit, even in their toe, there is one Pandu, there is one Champa. There is always some bit of Pandu, there is some bit of Champa. Their love is so great. So same way, the north pole and the south pole can't be segregated, can't be separated. Even in an atom, even in an electron, you might say, sir, I have just one particle. Will there be north and south? Yes, if the electron spins, it generates its own north and south, they come simultaneously. But that is not the case with electricity. You can have a proton, you can have an electron separately. That is possible. It is possible to make magnets out of iron and alloys. We begin with the description. This is not so important. I mean, that is understood. These things you will see that iron and its alloys, okay, this thing what we are saying, it is possible to make magnets out of iron and alloys. This thing you will see are basically ferromagnetic materials. Slowly after this chapter proceeds, you will see the different types of materials. We also talk about Gauss's law. We also follow it about Earth's magnetic field. We describe how magnetic materials can be classified, blah, blah, blah. They are just telling what are we going to do in this chapter. Okay, let's talk about the bar magnet. One of the earliest childhood memories of the famous physicist Albert Einstein was that a magnet gifted to him by a relative. What did you get as a gift? I never got magnet as a gift by some relative. I would have hated that relative if somebody gifted me magnet. But okay, Einstein loved it. I got 10 rupees or 20 rupees. Hey, I'm leaving. I'm your auntie. Take 20 rupees. These days, I think kids get 500 rupees or 100 rupees or maybe some gift or 1000 rupees. I don't know. What was your gift? Did you get a magnet as a gift from some relative? At least I did not get. Einstein was fascinated and he played endlessly with it. He wondered how the magnet could affect objects such as nails and pins away from it and not in a way connected by spring or sling. We begin our study, blah, blah, blah. Okay. So the pattern of iron filings suggests that the magnet has two poles similar to positive and negative charge of electric dipole. As mentioned in the introductory section, one pole is north, one pole is south when suspended freely. Again and again they repeat the same thing. A similar pattern of iron filings is observed around a current carrying solenoid. Okay. So let's have a look. Yep. Oh, thank God. So I am considered as normal as you guys then. So I did not get fascinated. Cool. Thank God. I thought I was abnormal because Einstein got fascinated. I was also fascinated, but no relative gifted me. That's all. Anyways, now the pattern of the iron filing suggests that the magnetic A bar magnet has two poles, one positive, one negative, just like the charge of a dipole, positive, negative charge. Similarly, the pattern suggests there are two polarities. When suspended freely, the point approximately, okay, all right. Now, see guys, if you take a sheet of paper, okay, if you just take a sheet of paper, you sprinkle iron filings on it. Iron filings get affected by Earth's magnetic field or bar magnet's magnetic field. You place below this some bar magnet, It is a magnet which is having north pole and south pole. And you tap this paper, tap, you tap it. So these iron filings are free to move, then they will start aligning themselves in the magnetic field of that bar magnet. You will see the pattern looks something like this. This suggests that, it feels as if they are coming from somewhere, going somewhere, and they are also passing within the magnet. So this point, one was called a south pole, the other was called the north pole. Now, who is decided north and who is decided south? It depends on how they align with the earth. So the pole which is closer to the Earth's north pole was called north pole. The pole which is closer to the Earth's south was called as the south pole of that particular magnet. So this is also representing how the magnetic field is around a bar magnet. All right. So they also say that, listen, this pattern is similar to a current carrying solenoid, because at the end of the day, what is a solenoid? A solenoid is an electromagnet. Whereas the actual magnet over here, this is nothing but your permanent magnet. You don't need to turn on electricity. A bar magnet does not need a switch. It is always a magnet. It's once a magnet, always a magnet, right? They say once a Vedan, always a Vedan. That means once you are a Vedantu student, you are always a Vedantu student, no matter where you go, no matter which college you graduate from. So that's a permanent magnet. Electromagnet is where you turn on the electricity, then it behaves like a magnet, otherwise it doesn't. So electromagnet is like a solenoid. Now, the magnetic field lines. How do the magnetic field lines look like? We have seen this before, but again, it's like a revision, or we are again revisiting this. So, the pattern of the iron fillings permits us to plot. My God, we have to take permission from it. So guys, we took permission from the iron fillings to plot the magnetic field lines. This shows both for the bar magnet and the current carrying solenoid. For comparison, refer chapter 1. Why do they talk like this, as if they are writing some law book? Chapter 1, this figure, electric field as in this figure. Okay, I think these people are lawyers who wrote this book, at least this paragraph. The magnetic field lines are a visual and intuitive realization of the magnetic field. Their properties are blah blah blah. Now they start with the properties. Observe this carefully. This is for an actual bar magnet. This is for basically, an electromagnet. So basically an electromagnet, basically a solenoid. And this one is for electrical charges. They all look similar, but there is some difference. Same, but different. Same, for different. What is it? If you observe, see, for the bar magnet and for the electromagnet, it is very similar. Even the field lines continue inside the magnet. But that's not the case for electric dipole. They originate from the positive, end at the negative, but they do not continue inside. Rather, they start from the positive and end at the negative. It's not the case with an actual magnet or an electromagnet. They do not start from north and end at south. There is no start and there is no end. It's always closed loops. But for an electrical dipole, it is never a closed loop. There is a start, there is an end. That's what you will see. So, the most important property is over here. Magnetic field lines, are continuous closed loops. Very, very important. Unlike the electric dipole, where the field lines begin from the positive charge and they end on a negative charge, or they can even escape to infinity. If you take a point charge, the electric field lines go till infinity. For a negative charge, they come from infinity onto the negative charge. So there is a start, there is a end for charges, but for magnets, there is no start, there is no end. One of the most important property. Yeah, I hope this is absolutely clear. The tangent to the field line given at a point represents the direction of the field. This is again another important property. The tangent to the field line represents the direction of the net magnetic field. Makes sense. Think about it. If you have a, I don't know why this diagram is over here, but anyways, if you have this magnetic field, if you draw a tangent, then the direction of the tangent gives me at that point where is the magnetic field. So drawing a tangent helps me get the direction of the magnetic field. The large number of field lines crossing per unit area, the stronger the field is. So in figure 2.8 where the field is strong versus where the field is weak. So large number of field lines crossing per unit area, the stronger the magnitude of the magnetic field. So in this previous diagram, can you see over here the field is going to be strong versus if you go over here or here the field is weak. Same thing over here, guys. Here they are very close, so it is very strong, versus here there are fewer field lines per unit area. So the field strength depends on how many field lines are there per unit area or how close they are to each other. That is the density of the field lines. Obviously, magnetic field lines never intersect. Magnetic field lines will never intersect, because if they did, then at that point of intersection, I will draw two tangents. So which one is the correct direction of the magnetic field? Which one is the correct direction of the magnetic field? So such confusion can't happen. If there is a magnetic field, there is a unique direction of the field. So that's the reason why they should never intersect each other. One can plot the magnetic field lines in variety of ways. One way is to place a magnetic compass at different places, and this gives us an idea of the magnetic field direction at various points. Okay, fine. So if you are really jobless in life, you can do this instead of this. So what happens here is you pour the iron fillings on a sheet, you tap that sheet, the magnet below aligns all the iron filings in the field direction. So this is easy way. Another way is you can also take a magnetic needle and you can go around and you can see where the magnetic needle is pointing. If it is pointing there, you go there. If it is pointing there, you go there. If it is pointing here, you go there. You go in wherever direction it points and then you draw that curve that gives you the magnetic field line. And you can keep going at different places, you will get different field lines. So that is a little bit tedious, longer way. So after the NEET exam, when you have lot of free time, then you can definitely do this method where you can run around with a magnetic compass and then you can draw the magnetic field line. Okay. Yes. Moving ahead. Bar magnet as an equivalent solenoid. In the previous chapter, we have explained how a current loop as a magnetic dipole. We mentioned Ampere's hypothesis that all magnetic phenomena can be explained in the form of circulating currents. This resemblance for a bar magnet and solenoid suggests that a bar magnet may be thought of as large number of circulating currents. In analogy with the solenoid, cutting a bar magnet in half is like cutting a solenoid. We get two smaller solenoids with weaker magnetic properties. Field lines remain continuous, emerging from one face to the other. One can test this analogy by moving a small compass needle in the neighborhood and a current carrying long solenoid. Noting the deflections of the needle are similar in both cases. To make this analogy more firm, we calculate the axial field of a long solenoid depicted by this, and we shall demonstrate at a large distance this axial field resembles of a bar magnet. This is also the far axial magnetic field of the bar magnet, which may be obtained experimentally. Thus, a bar magnet and a solenoid produce similar magnetic fields. Bar magnet and a solenoid produce similar magnetic fields. The magnetic moment of a bar magnet is thus equal to the magnetic moment of a bar magnet is thus equal to the magnetic moment of an equivalent solenoid that produces the same magnetic field. Explained how a current loop acts as a magnetic dipole. Okay, and yes, now okay, cutting a bar magnet in half is like cutting a solenoid. We get two smaller solenoids with weaker magnetic properties. Okay. Okay, and lastly over here, the resemblance of magnetic field lines for a bar magnet and a solenoid suggests that bar magnet may be thought of as a large number of circulating currents. Okay, so what do these lines basically mean? In the previous chapter number 4 only, we have done this, if you remember this properly. If you take a coil, okay, if you take a coil like this and you pass some current in it, the current goes like this, the thumb goes this way, so you will see that the magnetic field lines will go like this. This is how the magnetic field lines look like for a coil carrying current. This is for a coil carrying current. If you take it as many coils, if you take many such coils, one after the other, then what you get is basically nothing but a solenoid. If you put many such coils together, this is nothing but a solenoid which has some current passing through it, with a current I passing through it, and it also generates a very similar magnetic field around it. So I might have to draw a few more so that it looks like a solenoid. Like this. So you will see that the magnetic field lines go around like this. They obviously even pass through the solenoid. I'm just not showing them, but it is there. So there is definitely a north pole here, south pole here. This is the north pole, this is the south pole. And now comparing this with the actual bar magnet, with north pole and south pole, the field lines look very similar. The field lines look very similar. So that's the reason why they say in this paragraph that a current loop acts like a magnetic dipole. A current carrying loop acts like a magnetic dipole. The magnetic dipole moment formula, if you remember, it was number of turns into current into area. Number of turns into current into area. That was the magnetic moment. Do you remember this, guys? Everyone? Very clearly, we have discussed this. So even a solenoid is like a bar magnet. Now, if you break a magnet, it's like cutting a solenoid. It's like breaking a solenoid, and you are getting two smaller solenoids. Each of those smaller solenoids will also have individual north pole and south pole. That explains why whenever you break a magnet, you always end up getting a north and a south pole. Right? That's why you always end up getting a north pole and a south pole. So whenever you cut a bar magnet, it's like breaking that solenoid into smaller parts, but that solenoid will have, a lesser length, so you will get a smaller or weaker magnet. So the magnets keep getting weaker and weaker if you keep breaking it into smaller pieces. And all these things also point to that the magnetic field lines of a bar magnet and a solenoid look very similar. And that is the reason why the bar magnet and solenoid, because they produce similar field lines, the moments will also be similar. The magnetic moments will also be similar. So guys, this magnetic moment and this magnetic moment, because the field lines are very similar, it will be identical in nature. In fact, we have seen how to calculate the magnetic field on the axis of a solenoid. magnetic field on the axis of a solenoid or on a bar magnet. How to do that? Well, do you remember electric dipole? Positive, negative charge. If you go on the axis, what's the electric field formula? 1 by 4 pi epsilon naught, 2 times electric dipole moment by the distance cube. So same thing is applicable here. Instead of 1 by 4 pi epsilon naught, you have mu naught by 4 pi. Instead of 2 times of electrical dipole moment, you have 2 times of magnetic moment. And instead of the distance, it's the same thing, but you will have x cube over here. So x being the distance from the magnet. This is the point where you are trying to find the magnetic field. Looks very, very similar. This formula can be used for this. It can be also used for this. It can be also used for this. So everywhere you can use this formula. Is this absolutely clear? Thank you, Madhumati. Everybody clear about this particular statement? That is what they have mentioned. Mu naught by 4 pi 2m by r cube. Here they are using the symbol m, okay, small m, but you can also use capital M symbol, because some books use capital M because small m might look confused with mass or some other term. So that is what they have put down over here. Great. Now the next step. The dipole in a uniform magnetic field will also experience a torque, and there is also some potential energy associated with it, and they have done the calculation for this. So let's understand it. See guys, when you have a magnetic moment, that means there is a north pole, there is a south pole, and you place it in some external field. This is external magnetic field. Then there is a torque acting on it. And that torque is given by basically magnetic moment cross the magnetic field. If you want the magnitude of it, the magnitude of the torque is basically mb sine theta. It is nothing but your magnetic moment into the magnetic field into the sine theta. This is what the torque is. This same formula was also there in electrostatics, if you remember correctly. Torque was electric dipole moment cross electric field, which was nothing but Pe sine theta. Instead of electric field, you have magnetic field. Instead of electric moment, you have magnetic moment. That's the only difference. Otherwise, everything is very, very similar, but different. Same, but different. Now in electrostatics, you also had the formula for energy stored in it. There was also a formula for energy stored in it, but that was electrical energy. Now we will be talking about the magnetic energy. How much is the magnetic energy of the dipole in that external field? Instead of the dot product of electric field moment into the electric field, here you will have nothing but magnetic moment dot producted with magnetic field with a negative sign. So if you expand this, it will become minus mb cos theta. If you do cos theta, you basically get the magnetic energy stored. So that's it. So this is our formula, guys. This is for energy stored, and this is obviously for the torque. That is exactly what they have mentioned right over here. They have calculated it. It is minus m dot b. Torque was m cross b. So this formula is the magnetic potential energy which is stored. Okay, very, very important. Let's understand this through simple examples. Imagine there is a bar magnet with a moment of 10 ampere meter square along the field of 0.3 0.3 Tesla. 0.3 Tesla. If it's rotated by 120 degrees, find the work done and the new torque on it. Find the work done and the new torque on it. Let's understand this problem. There is magnetic field like this. Earlier, our magnet was aligned in the direction of the field. Later on, that magnet has been rotated by 120 degrees like this. Okay, so you can think as if the magnetic moment was here. Now the magnetic moment has shifted. Okay, so earlier the magnetic moment was here. Now the new magnetic moment has shifted. This complete angle is 120 degrees. So let's try to do this problem. Very easy, guys. If the first question says find the work done, to find the work done, I need to find how much did the energy change. This magnet, when it is aligned in the direction of the field, it has some energy. We can find that out. So that initial energy will be minus m into b into cos 0, because it is perfectly parallel. Angle between these two vectors will be 0 degree. So therefore it will be nothing but minus mb. Cos 0 is nothing but 1. We'll do the substitution part later on. If you talk about the final energy, it is minus mb cos, the total angle is 120 degrees. What is cos 120? If you remember correctly, cos in the second quadrant, 120 is second quadrant, it is negative. In fact, cos 120 will be negative half. Cos 120 will be nothing but negative half. So put minus half over here, minus minus becomes plus, so it will just become mb. That's not the concern. The question is find the work done. Work is always final minus initial potential energy. This is external work done. It is plus delta U. If you remember correctly, we have seen this in electrostatics and numerous other places, even in work energy. It is just delta U, not minus delta U. That would be conservative forces work done if I put minus. So it is final minus initial. What is the final potential energy? It is mb. What is initial potential energy? It is nothing but minus, sorry, I forgot that 2, guys, sorry, mb by 2. So this was nothing but mb by 2 and this is just minus mb. So minus minus becomes plus, half plus 1 is 3 by 2. So it will become 3 by 2 mb. So what is that value of m that we know? It is 10 amperes meter square. Magnetic field is basically 0.3 Tesla. So basically 3 3s are 9. 9 by 2 is 4.5. 4.5 into 10 is 45. Again multiplied by decimal will again make it 4.5. So 4.5 joules of external work needs to be done. 4.5 joules. How many of you got it? Everyone? Clear till this point? Everybody clear till this point? All right. What about the next part of the question which says find the torque? Torque is mb sine 120. Magnetic moment 10. Magnetic field 0.3. Sine 120 is positive root 3 by 2 because 120 second quadrant, sine is positive. Okay. 10 into 0.3 is 3. So it will just become 3 root 3 divided by 2 Newton meter. So that is the torque acting on it. 3 root 3 divided by 2. Clear how to solve these kind of questions? You will definitely find these kind of questions in your NEET paper as well. Great. Moving ahead now to another NCERT question. Shows small magnetized needles placed at point O. The arrow shows the direction of its magnetic moment. The other arrow shows different positions of the magnetic moment of another identical magnetized needle, in which configuration the system is not in equilibrium, which is stable, which is unstable, which is corresponding to lowest energy, and all of that. Now, in order to solve that question, you should recollect our previous discussion of electric dipoles alignment and their equilibrium configurations. Imagine this was magnetic field pointed like this, and our magnetic moment first time is aligned, next time is perpendicular, next time it is like this. This is our magnetic moment. In the first case, basically theta is 0, second case theta is 90 degrees, third case theta is 180 degrees. So what will happen to each one of cos and sine values? Cos 0 is 1, sine 0 is 0. Here cos 90 is 0, also means sine of 90 will be 1. Here cos 180 is negative 1 and sine of 180, sine of 180 degrees is basically 0. Okay. This will be useful for our torque and potential energy calculations. Let's start with torque first. If you measure the torque, in this case, torque is mb sine theta. mb sine theta, because sine theta will be 0, therefore the torque will also be a big fat 0. Here also sine 180 is 0, so here also the torque will be 0. Here sine 90 is 1, in fact this torque will be maximum and it will be just mb. Now what do you see over here? There is no torque acting. Here also there is no torque acting. So such situations, when there is no torque, that means if you leave it, they will stay as it is. So that is basically a condition for equilibrium. Equilibrium. This is also equilibrium. Now there will be multiple types of equilibrium. Just imagine somebody is nicely sleeping on this nice surface over here. This is our Pandu, who is a sleeping Pandu. So we have got a nicely sleeping Pandu. His eyes are closed. Just imagine this. Versus another Pandu who is sleeping on the top of a hill somewhere over here. Carefully they have been placed. If they are placed there, they will stay there as it is. Nothing will happen to them. They are in equilibrium, yes or no? This Pandu is sleeping inside a valley or a bucket like thing or a bowl or a, some bed sheet which has been tied to the trees, okay, like a hammock. And this person is sitting on or sleeping on the top of some mountain on a peak or somewhere. Both are in equilibrium. But let's say some dream comes, they get disturbed in the dream. So Pandu moves. If Pandu 1 versus Pandu 2, Pandu 1 gets disturbed and moves, rolls over here or here, what will happen? The gravity will pull him back over here. So when disturbed, you get pulled back to your original equilibrium. So that is definitely going to be stable. This Pandu gets some dream. He dreams about Champa being caught by a dragon and the dragon is flying off in the air. And when Pandu tries to catch the dragon is blowing out hot gases. So that dream comes like a nightmare. So this Pandu gets disturbed, he shakes. If he moves here and there, he will start rolling down the mountain. He will start rolling down the mountain. So definitely it is going to be unstable equilibrium. Here this Pandu had more potential energy. Here this Pandu had less potential energy in this locality. So whenever potential energy is high in that locality, then you can say it is unstable equilibrium, provided all the other forces and torques are 0. And when the energy is low in that vicinity, then assuming the torque and forces are 0, then it is said to be stable equilibrium. Correct? Yes. So coming back to this, if you measure the potential energy here, it will be minus mb cos 180 is negative 1. So hence this would be positive mb. Here if you measure the potential energy, it is cos 90, which is 0. Lot of you might think, sir, this is the least energy. Wrong. Look over here, minus mb, cos 0 is 1. So it will be minus mb over here. A negative number is lesser than 0. So this is the least energy and this is the maximum energy. From this, you easily understand this equilibrium over here, because less energy is definitely going to be stable, whereas this equilibrium will be unstable because of the large energy. So this is unstable equilibrium. So for stable, the field and the moments are aligned. For unstable, they are anti-parallel. And when it's perpendicular, it's not a equilibrium. It's just the torque is maximum and the energy is 0. Is this point absolutely clear? Everyone? Okay. Glad you liked that explanation, Krishna. Now you'll never forget about the dragon, kidnapping Champa, and blowing hot gases. Hopefully you guys get that dream today. It will be nice. Fantasy world. Okay, coming back to this particular question over here. In which of the following configuration it is not in equilibrium versus blah 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 equilibrium. So guys, see over here. A small magnetized needle P, which is placed at point O. This is a magnetized needle. Oops. So that magnetized needle, which means the north pole will be here, south pole will be here. It will be generating magnetic field around it. It will be generating magnetic field around it. So one of the magnetic field line will just go like this. Say for example, will go like this. Oops. Other magnetic field line will come like this. Then more magnetic field lines are there. They will go like this before coming back over here. There will be also magnetic field lines going like this. I hope this is very, very clear. So there are multiple other things over here as well. Even at this point, the magnetic field lines will be perpendicular. So I've shown all the magnetic field lines everywhere for this magnet, this magnet, this magnet, this magnet, this magnet, and this magnet. Now observe carefully what are the angles at every place. If you look at Q4, magnetic field and magnetic moment are opposite to each other. So I'll start putting the angles over here very quickly. So it is basically 180 degrees. Here it is in the same direction, so it is 0 degrees. Here it is opposite to the field. Magnetic moment is up, magnetic field is down. So it is basically 180 degrees. Here the magnetic field is in the direction of the moment, so it is 0 degree. Here it is 90 degree. So here it is 90 degree. I think you got your answer now. Wherever it is 0 degree, wherever it is 0 degree, what will be the answer? Wherever it is 0 degree, the answer will be, it will be in stable equilibrium, minimum potential energy. Wherever you see it is 180 degree, 180 degree, what will be the answer, guys? The answer will be, it will be unstable equilibrium, no torque, potential energy will be maximum. Wherever you see 90 degree, wherever you see 90 degree, what will it be? The torque will be maximum, energy will be 0, but it is in neither kind of equilibrium. So that would be the answers of this particular question. Lowest potential energy, wherever the equilibrium is stable. Unstable, that's where it would be maximum. Okay, thank you for reminding me to have water. Yes. So just check your answers. Everybody got this? So this chart is very, very important. This should be there in your notes. Okay, this should be definitely there in your notes. And if you are wondering, sir, can you give me ready-made notes? Then I'll give you ready-made notes. You don't have to do anything. You just have to click few buttons and you can order these flashcards at your doorstep. These flashcards are truly amazing. This flashcards has every single thing that you want. Look at this. I just plucked out a random flashcard. It has got the moment of inertia formulas for all the geometries, beautifully looking diagrams, and angular momentum, volumes, everything over here. So this is just like a rotational motion flashcard. So there are many such flashcards, guys. Such nice things. Okay, you can see right over here. So this is your magnetic field flashcard. Right over here you can see Biosavart's law, magnetic field for solenoid and long wires and circular loops. Amazing. So you can order them. I have already made a video for this, just a couple of days back. Okay, moving on to the next thing. This we have already seen, the electrostatic analog. I think I just told this to you. The magnetic field on the axis formula looks very similar to the, look at this over here. The magnetic field on the axis looks very similar to the electrostatics formula, where you have an electric dipole and you find the electric field on the axis. It's just that mu naught by 4 pi is replaced by 1 by 4 pi epsilon. Magnetic moment is replaced by electrical dipole moment, and magnetic field is replaced by magnetic field. So there is a lot of similarity between all of them. So that's why we can say it's like same but different. So what are the things? Electric field replaced by magnetic field, magnetic moment replaced by electric dipole moment, 1 by 4 pi epsilon naught replaced by mu naught by 4 pi. So everywhere you will see that this holds true. This basically holds true in electricity and magnetism. In fact, you can go back a little and you can say, sir, if this was the magnetic field on the axis, then do I really know the magnetic field on the equator? The answer is yes. The answer is yes. Definitely you know the magnetic field on the equatorial region. Remember, this was the equator, and the magnetic field on the equator will be very similar. Instead of 1 by 4 pi epsilon, you will have mu naught by 4 pi. Instead of 2m, it will be just m. Remember it. It is half on the equator as compared to the axis. And this distance, if it is y, it will be divided by y cube. So this is the magnetic field formula on the equatorial region. If you remember, on the axis it is always double. On the equator it is always single times. Yeah, there is a difference of that numeric 2. Yes, there is a difference of that numeric 2. That's exactly what they have mentioned over here, if you notice carefully. On the equatorial region it's m, but on the axial region there is 2m. So this is basically 2 times of magnetic field on over here on the equator. Okay, keep this in mind. Is this clear, guys? This is just reiterating, re-emphasizing again and again the same thing, that electricity and magnetism are same but different. Only the variables have changed. All right, let's basically now see the complete chart of the analogy for all the different things in electrostatics and magnetism. So wherever you had 1 by epsilon naught, you will have mu naught. Wherever you have epsilon naught, you will have 1 by mu naught. That's the same but different thing. Dipole moment P, magnetic dipole moment M. Field formula, torque formula, everything. Field, torque on a dipole P cross E, torque on a magnetic dipole M cross B. Energy of a dipole minus P dot E, energy of a magnetic dipole minus M dot B. Even the axial field and the equatorial field formulas are very similar. That is what this is telling us. So let's probably do some simple questions on this. If a coil of 100 turns and 0.2 meter square has a current of 2 amperes, or let's say 5 amperes, find the field at a distance of 4 meters on the axis and 2 meters from the center in the plane of the coil. This is the question. Very, very nice question. Many students will get confused at some or the other place. Let's try to solve this. Okay. First, let's draw the coil. This is our coil, and this is our axis of that particular coil. If you see, there will be also y-axis, there will be also z-axis, something like this. Visualize this in 3 dimension, guys. Visualize this in 3 dimension. First time I am standing at a distance of 4 meters on the axis somewhere over here. So at this point, I should use the magnetic field on the axis formula. The next says 2 meters from the center in the plane of the coil. Now, if you want to visualize the plane of the coil, visualize like this. This is that plane of the coil. Are you able to visualize this? Just quickly think and tell me. Are you able to visualize the plane of the coil? It is basically your YZ plane. Just tell me, are you able to visualize that plane of that coil? So from the center in that plane of the coil, you are at a distance of 2 meters. So that means you are basically somewhere here, maybe here. And this point is obviously an equatorial point. Why is it an equatorial point? Observe this carefully. Because a coil carrying current behaves itself like a magnet, where this is the north pole and this is basically the south pole. So you can clearly see the magnetic moment is right over here. And that is why this is axial point, this is perpendicular, so that's why this is equatorial point. Is this part of the problem visualization wise clear? Absolutely. Everyone? Okay. Yeah. Great. Sir, flashcards details solunga sir. Saravana? You can watch it here. It's there right on our channel. Okay, it's there right on our channel. You can just go back a little bit, go to videos, and where is it? NEET flashcards are here. Just check this out. Say bye-bye to your notes. Okay, it's right over here. Just check this out. Okay, you can order using the link which is given in the description box of this particular video. NEET flashcards. Click on this link and it will open up this particular page. You can say buy it now and it will be delivered to your address, which you will be putting it up right over here. Okay, as simple as that. So let's start doing the question. First, let's do it for the axis, but before that I need the magnetic moment magnitude. It is, remember, NIA, number of turns 100, current, how much is it? It is basically 5. Area, how much is it? It is basically 0.2. 5 2s are 10, decimal goes away. So it will be basically 100 ampere meter square. That is the magnetic moment. Okay, let's do the formula for axis. So at the axis, it is mu naught by 4 pi 2m divided by x cube. Mu naught by 4 pi is 10 to the power minus 7. 2 into m, m is basically 100. X is the distance, so that is basically 4 cube. Great. So what do I get? This is 10 raised to 2. 10 raised to minus 7 will make it 10 raised to minus 5 into 2 divided by 4 cube. 4 square 16, right? Into 4 will make it 64. So it will be 1 by 32. So it will be basically 10 raised to minus 5 by 32 Tesla. So that is the magnetic field on the axis. That is the magnetic field on the axis. Perfect. Yeah. Krishna, Kwanjam, Terida. Yes, I can understand a little bit because I do watch Tamil movies, right? I've been a fan of Tamil music, Tamil movies, their stories. I mean, they are very, very different. It's not the same old things. There are some directors and some actors who have done exceptionally well jobs. So thanks to the movies, I understand it, right? And I was born in Tamil Nadu also, right? Yeah. Anyways, coming back to the equatorial formula, it's the same thing, whatever you get on the axis, but exactly by 2. So whatever you got here divided by 2, so it will be 1 by 32 into 10 to the power minus 5 Tesla. So that's the magnetic field at that, but a lot of people forget this will only work if the distance is same. If you notice, this distance was 4, this distance was 2, so that's why it will not work. So just don't divide randomly by 2. That is a common silly mistake. See the distance. This is 2 meters, that is 4 meters. So obviously this will change. So you have to redo the entire thing. There is no other option. Mu naught by 4 pi. You just have m, and here you have y cube. This is 10 to the power minus 7. Magnetic moment is 100. Distance is basically 2. So 2 cube. So this will make it 2 cube, which is nothing but 8. So 1 by 8 into 10 to the power minus 5 Tesla. That's the magnetic field on the equator. Is this now absolutely clear how to solve these kind of questions? Oh no, Sumi, I don't know Bengali. Yeah. Thank you, Krishna, for all the respect from Tamil Nadu. Oh, by the way, we are going to do something really amazing for now. Yeah, students from Karnataka and students from Maharashtra, something really is amazing is going to come up. Yep, it's not what you are thinking. It's not exactly a Kannada channel. Well, it's going to be really cool because in Karnataka we have all kinds of students. We have students from Andhra, we have students from Tamil Nadu, we have students from obviously the original Kannadigas, and some Maharashtrians, some students from abroad. A lot of people who move abroad, when they come back to India, they usually settle down in Bangalore because of, it's got the title of Silicon Valley. And why not do something for all the Kannada students, because there are a lot of engineering and medical colleges in Karnataka, and 9th and 10th standard students too, right? So something really cool is coming up for all of you. Stay tuned for your KCT COMEDK exams, and also for Maharashtra students, especially like when 6 to 7 lakh students write the CET exam, and when nobody cares about them, and me being, a student from Maharashtra, I think I should do something. So something really cool is coming up, so stay tuned, guys. So for Tamil Nadu students, we already have a Tamil channel, right? Shimon sir is obviously taking care of the Tamil channel very beautifully. You have the V Master Tamil, you have, I think, the Tamil JEE and the Tamil NEET as well. So we have the Telugu channels as well for Telugu JEE, Telugu NEET, and also the board students, which is just the Vedantu Telugu channel. Now it's time for the other states to experience the best of the best teachers. Yes, don't worry, West Bengal and Kerala and other states also, it will come. We already have a Punjabi channel now, yep, for Punjabi students, right? So guys, it shows that Vedantu really cares for everyone. Yes, Sukanya, it will be Swalpa Kannada. Yeah. Okay, moving on to the next point, which is magnetism and Gauss's law. And there is a huge paragraph given over here. Magnetism and Gauss law. We studied Gauss law for electrostatics for closed surfaces. Number of lines leaving the surface is number of lines entering it. This is consistent with the fact that no net charge is enclosed. However, in the same figure for a closed surface, there is a net charge outwards. Since it does include a positive charge, situation is radically different for field where continuous field lines and closed loops are formed. Both cases visually demonstrate that number of field lines leaving the surface is balanced by the number of lines entering it, as the net magnetic flux is 0 for the surface. This is true for any closed surface. Very important. So that number of magnetic field lines leaving the surface is balanced by the number of field lines entering it. So the net flux is basically going to be 0 for the surfaces. This is true for any closed surface, okay, and therefore we get this particular formula, okay. Oh sorry, not this one, this was electrostatics. So the net flux is given by this, and the difference between Gauss law and magnetism, that for electrostatics is a reflection the fact that isolated poles called monopoles are not known to exist. There are no sources or sinks of B. The simplest magnetic element is a dipole or a current loop. Okay, again some critical points. There are no sources or sinks of magnetic field. The simplest magnetic element is a dipole or a current loop. All magnetic phenomena can be explained in terms of the dipoles or current loops. Thus, the Gauss law for magnetism is saying that the net magnetic flux through any closed surface is 0. Okay, so let's understand this, guys. See, if you take an electric charge system, okay, so there is some electrical charges over here, positive, negative, and there will be a lot of electrical field lines which might be coming out of it, maybe like this. And if somebody takes a Gaussian surface, if you take a Gaussian surface, means a enclosed surface, there is no opening in it, there is no hole in this thing, then if you do the electric field, dot area, electric field dot producted with the area, what you get on the right hand side is nothing but how much ever is the charge enclosed divided by epsilon naught. This was nothing but Gauss law in electrostatics. Now let's do the same thing for magnetism. For magnetism, the electric field lines never start, magnetic field lines never start or they never end. That means there is no source nor there is sink. Source means it originates, sink means it terminates. For electricity, there is always a source and there is a sink. On the negative charges, the electric field lines will definitely terminate, maybe, right? The electric field lines might definitely terminate, but that's not the case. That's not the case for magnetism. So you will see for magnetism, the magnetic field lines will always be closed loops. It will always be closed loops. So that's how the magnetic field lines are. Which means if somebody draws a Gaussian surface again, just like they have drawn here, which is a closed surface, and at every point you measure the magnetic field and do the dot product, just like you have done here for the entire surface, just like you have done it over here for the entire surface, you put that closed integral. What is this symbol called? Closed integral. Means you cover every part of that surface. Don't leave anything. That is called as a closed surface integral. Okay, that is called as the closed surface integral. I have already given you that example, of your mom asking you to clean the room. If your mom says clean the room and she puts that symbol D, that means you have to clean a small part of the room. If your mom says clean the room from A to B, that means you clean from that corner to that corner. But if your mom says, listen, do this, declean cyclic integral, then that means you have to clean entire room. Don't leave one surface also. If you leave one surface, you will get one flying slipper on your head. Got it? So if your mom is little bit mathematical or your parents are mathematical, and if they say that, listen, cyclic integral declean, you should know what you should do. You should not leave anything. Okay? So try it out with your younger brothers or sisters next time. Just tell them cyclic integral declean. Cyclic integral D clean. They will be shocked. They will complain. Mom, dad, I think my elder brother, elder sister has gone mad. They are telling cyclic integral D clean. But that's okay. You understand me. All right. So coming back over here, if I do cyclic integral of the magnetic field dot product with the area at every single point, on the right hand side, I should not get anything, because no matter which area I choose, the amount of north pole and the amount of south pole are always in equal quantities. So the north polarities cancels the south polarities. They are always in equal amounts, and hence the net charge of magnetism will be 0. So this law is basically called as your Gauss law in magnetism. Gauss in magnetism. Gauss law in magnetism. What is then the definition of magnetic flux? The definition of magnetic flux will be like this. So magnetic flux, guys, if you have some area over here, and this is the area vector. This is the area vector, and you find that there are some magnetic field lines piercing through it, maybe like this. Then our magnetic flux, which is also directly proportional to the number of field lines passing through, a surface. Yes. So guys, this magnetic flux phi is given by B dot A. Very, very important. That dot product can be also written down as cos theta. So here you put magnetic field, and here you put area vector. So BA cos theta, where theta is the angle between magnetic field and the area vector. So that is the formula for something called as magnetic flux, which is a quantity which describes how much is the flow of the field. If the flow of the field is more, it has more flux. If the flow is less, it has less flux. So the flow of magnetic field, that's why I'm saying it's proportional to the number of lines passing through a surface, is called magnetic flux. It is field dot producted with the area. If you ask me the unit of magnetic flux, it is Tesla into meter square, which is called as Weber, which is just called as Weber. So the unit of magnetic flux is basically Weber. Keep that in mind. Everybody fine till this point? Okay. So whenever you have a curved surface, instead of B dot A, it will be B dot dA and integration of it. That's all. So whenever you have basically a curved surface, there will be many teeny mini small area vectors at every place. These are the small dA area vectors, and at every point there will be some magnetic field which will be passing through that particular point. So the small flux d phi will be nothing but your magnetic field at that point and the area at that point. So the total flux magnetic flux will be integral of d phi. So that is why I will put integration of our magnetic field dot producted with our area vector. Magnetic field dot producted with the area vector, integration. And if it is a closed surface, then I will put a cyclic integral. That is the reason why the term on the left hand side basically represents nothing but the magnetic flux for the closed surface, which is then called as our Gauss law in magnetism. Is this very clear how this formula came? Yeah, because it is cyclic, that means closed. Integration of B dot dA means flux, because just field into area is the flux if it is constant. If it is a curved surface, if it is non-uniform for any random thing, then you will have to obviously integrate it by taking small parts of that surface. That's why dA is integration. Hence, the net flux is 0. That is what this whole paragraph says. Instead of summation, I have put integration. That's all. Okay. So, there are no sources or sinks. Magnetic simplest element is not a north pole or a south pole. It is always a dipole or a current loop. You cannot go smaller than that. You cannot separate north and south. The smallest thing that you can get in a magnet is a dipole in itself. Pandu comes with Champa. And that is why the Gauss law says in magnetism, net flux through a closed surface is 0. Net flux through a closed surface is 0, because whatever comes in has to go out. Whatever comes in has to go out. Okay, so that is Gauss law in magnetism. Great. Now comes the next part, which is magnetization, magnetic intensity, and all the other things which are associated right over here. These are basically some magnetic properties of materials. Okay. Now imagine a material, okay, which is made of many atoms. Each atom has so many electrons, protons, etc. These electrons are revolving. These protons are also maybe shaking here and there. So whenever these teeny charges move, what do moving charges create? Whenever charges move, they behave like currents. And what does current create? It creates magnetic field around it. So they behave like small magnets. So an atom itself is a small magnet because there are charges which are moving inside of it. So imagine so many atoms in an object, in a liquid, in a fluid, in a gas, in a solid. So many atoms, so many charges, so many random motions. Won't that create so many teeny magnets? So the material as a whole will be magnetic in nature. Now it depends whether the magnets cancel out each other or they produce a net field. That's another story. But yes, any material around us, even us, even the humans are made of small, tiny magnets. But yeah, the thing is, all these magnets end up cancelling each other. So that's why we do not behave like a normal permanent magnets. Or else, imagine if we were such permanent magnets, then somebody is walking past us, suddenly you will get attracted and both of you will stick. Or maybe you might just repel from a person. That would be really cool. Pandu would love it, because then Pandu would be the North Pole or South Pole and Champa would be the opposite pole. And then Pandu will see Champa is getting attracted to him, but it will not be because of his looks or because of his personality, but that is because of its magnetic properties. So we ourselves, although we are made of teeny magnets, there are no resultant magnetic property which is left in us. So we do not behave magnetic. But if there is a resultant magnetic property, then it will behave like a permanent magnet, like your normal magnets which you have. Yeah, is that right? Clear? Awesome. So now what do we see? Earth is, okay, first they talk as if they are writing Shakespearean language. The earth abounds with a bewildering variety of elements and compounds. Why do you have to do that? In addition, we have been synthesizing new alloys, compounds and even elements. So then they come to level. First they think they are Shakespeare. The earth abounds with a bewildering variety of elements and compounds, and then slowly they come to mathematics over here. We have seen that a circulating electron in an atom has a magnetic moment. In bulk, these moments add up and they can give a net magnetic moment, which is non-zero. We define the net magnetization of a sample to be equal to, okay, we have seen that circulating electrons in an atom has a magnetic moment. Now, when you go to a bulk material, these moments add up vectorially and they can give a net magnetic moment which is non-zero. So, magnetization of a sample is equal to the net magnetic moment per unit volume. Magnetization is net magnetic moment per unit volume. M is a vector. Yes, M is a vector with dimensions of per unit length and ampere. We'll come to that. Okay, it is measured in ampere per meter square. Sorry, ampere per meter. Consider a long solenoid, unit length carrying this, given by the magnetic field inside is given by mu naught Ni. If the interior of the solenoid is filled with a material with non-zero magnetization, the field inside the solenoid will be greater or will be different, and the net field will be B naught plus B. Okay, we'll come to this also. The net field will be B naught plus B. So the net field inside the interior of this solenoid may be expressed as this, and then they go to other things where Bm is the field contributed by the material core, where Bm is the field contributed by the material core. It turns out that the additional field Bm is proportional to the magnetization M of the material and is expressed as the following. Bm is mu naught into M, where mu naught is the same constant permeability that appears in Biot-Savart's law. Okay, let's have a look. What does this entirely mean? Starting off over here. Okay, imagine guys, this is our nucleus, and then you have this electrons which are basically orbiting the nucleus, These electrons are basically the charges in motion, are basically like small current loops. That means they are magnetic in nature, so I will call it as if they are small electromagnets, and hence it will behave like a magnetic dipole. So just imagine all the teeny mini charges inside any material will have their own magnetic moments. All these small teeny mini particles which are revolving here and there, they will have their own, small magnetic moments in random directions depending on their orientations. So magnetic dipole with a moment of small m, again magnetic moment of that particular particles. So all these magnetic moments, if you add them vectorially, what you get is probably the net magnetic moment of that material. This is the net moment of that particular material, which obviously is the sum of the magnetic moments of all the particles, is the net magnetic moment of all the particles added together. So then we get a term called as magnetization. Now here the symbols that they have used is slightly different. Instead of, see guys, they have used small m instead of capital M. That's the one major thing. They have used small m instead of capital M. That's all. So let me also use the same thing so that you do not get confused over here. So this is the magnetic moment of that material. Now if you divide it by the volume of the material, if you divide it by the volume of that material, what you get is basically, just think, per unit volume, what is the magnetic moment? Per unit volume. So if this is representing unit volume, how much is the magnetic moment present per unit that? So that is what is called as magnetization. Magnetization. So magnetization, M is nothing but your magnetic moment which you got upon nothing but the volume of it. The volume. That's it. The net magnetic moment per unit volume. Is this clear what magnetization is? Magnetization is how much moment is there, how much north-south polarity is there per unit volume. Okay, I hope this is very, very clear. Thank you, Krishna, for encouraging everyone to smash the like button. Like you can see over here, the numerator had a unit of ampere meter square. The denominator has a unit of meter cube in SI. So naturally, magnetic moment, when you cancel things, meters, you will be left with ampere per meter. Ampere per meter is the unit of magnetization. So if the magnetization is good, means for that unit volume, there are enough number of dipoles which are aligned in a particular direction. If the magnetization is zero, what does it mean? Means maybe they are all randomly arranged everywhere. So there is a possibility magnetization can be zero. For example, just think of this. Just think of these three things. Here, some materials are here, some is here, some is here, some is here. One is here, one is here, one is here, one is here. One is here, one is like this, one is like this, one is like this, one goes here, one goes here. So if you notice, for everything there is an equal and opposite thing. So the net magnetic moment will be zero, and also even our magnetization will also be zero. But imagine this. Versus this. If you see, most of the atoms moments are aligned in this direction. So the net magnetic moment here is high, whereas here the net magnetic moment, even though it is there, it is going to be low. So hence over here the magnetization is less, whereas here the magnetization is basically going to be more. Is this absolutely clear? When more and more are aligned in the same direction, it makes sense that the net moment will be more. If it is not, it's more random, then the magnetization will be definitely less. I hope this is clear. So that is what they initially define. Magnetization of a material is the moment per unit volume. Then they talk about placing this material in some external field, which is probably, let's say, generated by a solenoid or something. So the net field will be some value, and then they give this particular formula. It is convenient to introduce another vector called as magnetic intensity, which is defined by this. Okay, we'll come to that also. This is called magnetic intensity, which is defined by this, where h has the same dimension as m, and it is where h is measured in again ampere per meter, and then b will become nothing but mu naught h plus m. This is exactly from here. We repeat our defining procedure. We have partitioned the contribution to the field inside the sample into two parts. One due to external factors, one due to external factors such as the current in the solenoid. This is represented by H, and the other due to the specific nature of the material named by M. The later quantity, nature of the magnetic material divided by M, the later quantity is influenced by the external factors, and then they express this, okay, and then they get some more things. So guys, there are a lot of formulas over here. I'll explain it to you in a very simple manner. First, let me block all the important things over here. This B is also mu times of H, and they also define something called as susceptibility. It's a measure of how magnetic material responds to external field. Okay, we'll come to paramagnetic, diamagnetic, etc. And then they also relate permeability over here. The magnetic permeability is mu, same as the dimensions of mu naught. Okay, now I'll explain all this in a very simple way. Observe guys carefully. You have some material. You have some material. You have some external magnetic field. You have some basically external magnetic field. I will call that external magnetic field as B naught. This is your external magnetic field. When it passes through the material, then it might ask these small teeny mini magnets to move and rearrange, reorient, and because of that, the material itself might have its own magnetic moment. The material itself might have its own magnetic moment and its own magnetic field. This magnetic field is called as your induced field or magnetic field by that material. Magnetic field by that material. So usually the symbol for that is BIND or magnetic field of the material. Why did this come? Because external field is influencing it. External field is influencing it. So now think there will be a net magnetic field. Now there will be a net magnetic field. Sometimes, usually you use the symbol B only. This particular net magnetic field, won't it be the sum of our external field plus the magnetic field which is created inside our material, which is BM? Everybody understands this? The net field inside this will be the external field plus the field created within the material. All of them together will create your net field. So this is the first formula which you should know. Till this point, everything clear? Till this point, everything clear? Very good. Now, what happens is, they have also mentioned right over here, this magnetic field which is created inside that material is proportional to the magnetic intensity. Where is it? Magnetization is proportional to the magnetization, and there is a relationship between both of them. So that magnetic field is mu naught into M. Basically, it means if the magnetic moment is high, then even the field created by that magnet around it, will also be high, which makes sense. So therefore, magnetic field created by the material is proportional to the moment, and this is given by mu naught into m. That constant only is called as mu naught. That is what they have clearly told in this particular formula. This is experimental, completely experimental. Now, what happens is, how can you create the external field? The manner in which you can create the external field, many ways are there. You can use a solenoid, you can use another bar magnet, you can do anything. So many ways are there. So, if this external field, whatever this external field is there, if you divide this with the mu naught value, then what you get is basically your H, which is called as magnetizing field. Or basically magnetic intensity. So this is the formula for that. If you divide external by mu naught, you get the magnetizing field, and that is a vector quantity. That is basically the vector quantity. I'll give you a simple example. Imagine there is a solenoid and it has some current of 2 amperes and there are 100 turns per meter. Can we find the magnetizing field inside the solenoid? The answer is yes. H will be nothing but magnetic field which is there inside the solenoid by mu naught. But the magnetic field of a solenoid is mu naught Ni. So mu naught cancels and you will be just left with Ni. N is 100, current is 2. So the answer is 200 ampere per meter. So that is the magnetizing field of this solenoid. This is telling me how much I am trying to magnetize whatever is kept inside that solenoid. Whatever is kept inside that solenoid, how much I am trying to magnetize it, that is given by magnetizing field or magnetic intensity. The symbol is H. The symbol is H. Okay, this is what H is. It's a vector quantity. Now, the material itself will get influenced. The material itself will get influenced. We just spoke about it. The material itself gets influenced, and what does it create? It creates induced magnetic field, or basically magnetic field of that material. If you divide that with mu naught, what you get is magnetization. What you get is basically magnetization. What you get is basically magnetization. Very important formula again. Just like you divide external field with mu naught, you get H. Same way, if you divide induced or magnetic field of the material divided by mu naught, what you get is magnetization. Exactly the same thing which is written down over here. If you divide this with mu naught, you get magnetization. Till this point, everything clear? Till this point, everything clear? Okay. Now just imagine you have taken a solenoid. It has created its own magnetic field. In that solenoid, you place some material. That material creates its own magnetic field. So that's why inside that material, there will be a net magnetic field. That's why inside that material, there will be a net magnetic field. That has the contribution of the magnetic field of that solenoid, obviously, which is basically your external factor, and it also has the contribution of that induced field, which is because of that material. Does that make sense to you? Everybody with me on this? Clearly? Very good. Now, the formula for this magnetic field externally, I can just write it as mu naught into H. I can just write it as mu naught into H. The formula for this Bm, I can write it as just mu naught into basically M. And what I get is the net field, which is just your total B. So if you want, you can also write it down as mu naught and common, that is mu naught is just going to be a common thing. And then you have just basically H plus M. You have basically H plus M. So this is another simplification which is exactly mentioned over here. Mu naught into H plus M. If you rearrange this, you get this. You rearrange this, you get this. So there is no need of remembering this formula. If you remember this, automatically you can get this. You can automatically get this from this. Did you understand how this equation basically came? Did you understand how this equation actually came? Net field is mu naught into H plus M. Very good. Now, lastly, there are last few terms which we are going to define now. The last few terms are as follows. One thing is called as susceptibility. Symbol for that is X. It is nothing but susceptibility. X is defined as your magnetization upon your magnetization, whole thing divided by magnetizing field. If you notice, magnetizing field is nothing but how much field is given by the solenoid. That means how much you give. So it's like your input. How much field are you giving? How much you get outside? How much is it magnetized is what you are expecting. So that is like your output. So magnetization is your M. Magnetizing field is your H. Their ratio is what gives you X. So this is how susceptibility has been defined. Susceptibility has been defined. It is dimensionless, unitless quantity. Yes, thank you guys for reminding me. It is dimensionless and unitless quantity. Same way, there is also another quantity which is called as permeability, magnetic permeability. Magnetic permeability of that material, mu m, which is then defined as, the net magnetic field, divided by the magnetizing field, The terms look very similar, often very confusing. So magnetizing field, the symbol is H. Magnetic field formula is B. And what you get over here, that is nothing but your mu. So this is your magnetic permeability of that material. All these things you should definitely know. Magnetic permeability of the material. Now these terms can be used here and simplified further. How? Observe. We just saw that our B is nothing but mu naught into H plus M. So let's do one thing. Instead of B, let's put mu into H. Let's put mu of the material into basically H. Okay, as it is equal to mu naught into H plus M. Mu naught into H plus M. Divide the entire equation with H. Divide the entire equation now with H everywhere. With H. Let's see what do we get. H cancels, so we'll just be left with mu M. This will be mu naught and then I will have h by h is nothing but 1. M by h, you might be wondering what is M by h. M by h is nothing but susceptibility. It is nothing but your susceptibility. Perfect. So permeability of any medium is permeability in vacuum into 1 plus susceptibility. We got this. This is the important formula again. This is a very important formula again. If you know susceptibility, you can find permeability. If you know permeability, you can find susceptibility. And also we can do one small thing over here. Shift mu naught below. So mu m by mu naught will be 1 plus x. This is permeability of medium and permeability of vacuum. So this is basically called as your relative permeability. This is basically called as your relative permeability because it's just a ratio. So relative permeability is 1 plus x, or you can just remember this. It's one and the same thing. Okay. Either you remember this or you remember this. It's one and the same thing. So these are all the formulas which they have given, guys, in a little bit complex manner. So I have broken it down for you. So let's recap. Any charged particles revolving, they have a magnetic moment. Together, if you add the magnetic moments, you get the magnetic moment of the material. If you divide it per unit volume, it's called as magnetization. It is called as how much has it got magnetized, that is magnetization. Okay. And magnetization can be written down as how much field does it induce upon mu naught. How much field does it induce upon mu naught? Yes, it is also a vector quantity. It is also a vector quantity. How much field you give is called as magnetizing field, H. It is external field by mu naught. Using this and this, we get the total field as mu naught into H plus M. That is the net field. Further, we defined two additional properties of the material called as susceptibility, which is magnetization by magnetizing field, permeability as magnetic field by magnetizing field. Using these two, in this equation, we got permeability of the medium is permeability in vacuum into 1 plus susceptibility. That is what we got. Yes. Cool? Till this point? Great. So let's have a look at a question and then we'll come back. And then it's like hardly 15-20 minutes are remaining. We'll finish off this particular chapter. Okay. So yeah, we'll disperse for lunch break. A solenoid has a core material with relative permeability 400. The windings of the solenoid are insulated from the core and carry a current of 2 amperes. The number of turns is 1000 per meter. Calculate H, M, B, magnetizing current, everything. Okay. So first of all, guys, relative permeability is 400. Relative permeability is 400. That means mu relative, which is magnetic permeability of the medium by mu naught, that is basically 400. Okay. Solenoid is carrying some current. The turns are also given. Can you find H first? Yes, finding H is easy. H is nothing but external field by mu naught. External field is the field of the solenoid is mu naught Ni. So mu naught cancels. It just becomes Ni. So H will become number of turns per unit length, which is 1000 current 2. So therefore H will just become 2000 ampere per meter. Okay. Next, from here I get permeability of the medium is 400 into mu naught. I think H, mu are related to each other. H and mu are related to each other. Can you see this? Magnetic field mu m and H, they are all related to each other. So I can use this to find B. Therefore, since mu m is B by H, therefore B will be mu m into H. Mu m is 400 mu naught and H is nothing but your 2000. So that is what your H was. So you can substitute the value of mu naught also and you can get the answer. So 4 2s are 8. You have 2 zeros here, 3 zeros here. So it will become 5 zeros. Mu naught is basically 4 pi into 10 to the power minus 7. So if you want to write it like that, you can write it, or you can just leave it as mu naught. So that is our net magnetic field. So that is also done. Can we find M? Can we find M somehow? Just think about it. Can we find M somehow? Just think about it. Yes, is there a formula for M? Yep, let's go back. M is induced by mu naught. I need to find induced, but how do I find induced? That is the question, right? So over here, I know the net magnetic field. Okay, what do I do, guys? Think about it. To find out M, they would have done something like this formula. Remember this formula which we used over here? Yes. B is known, H is known, mu naught is known. You just have to find M. So use that formula over here. That's all. So our B is mu naught into H. H is nothing but 2000 plus your magnetization. In fact, this B also I already know. This B is 8 into 10 to the power 5 mu naught. Mu naught cancels. So you will just get 8 into 10 to the power 5 is equal to 2000 plus your M. So therefore M will be, yes, this was 2000, my bad, 2000. So M will be 8 into 10 to the power 5, guys. 10 to the power 3 is 1000. 10 to the power 4 is 10,000. This is basically like 1 lakh, right? So this is like almost like you have 1, 2, 3, 4, 5 zeros minus basically 2000, which is close to again 8000 only. Sorry, 8 into 10 to the power 5. Just check this out. Yeah, approximately the same thing. It will not change much. Yes. So that is also correct. Because if you subtract 2000 from 8 lakh, hardly any difference. It's going to be the same amount. So we found everything, guys, right over here. Is that clear, everyone? So we've used that formula. Yep. Now, they have put a term called as magnetizing current. The magnetizing current is that additional current that needs to be passed through the windings of the solenoid in the absence of the core, which would give a value as in the presence of the core. This is very important. This kind of question can come. The magnetizing current is the additional current that needs to be passed through the windings of the solenoid in the absence of the core, which would give the same value as in the presence of the core. What does this mean? What does this mean? See, this magnetic field which you got was when there was some material inside. But when there is no material inside, you will not get this much field. You will definitely not get this much amount of field. So, if you see how much external field you will get by just by just passing 2 amperes, it will be much lesser than this. So I will need some different amount of current to get the same field. So say for example, I write like this: to get that same field through that particular solenoid, mu naught n, number of turns per unit length, is basically 1000 into the current. I don't know, this is that new current which I need to pass. So guys, mu naught cancels. This is just 1000. So what will be my new current going to be? What is that new current going to be? 3 zeros cancel, 3 zeros cancel. So I'm left with 800. Okay, that's it. Mu naught has cancelled. So the new current is 800 amperes. If you pass 800 amperes, you will get back this same magnetic field. So how much is that extra current that I have to pass? That is called as the magnetizing current. That is nothing but 8000 amperes. Earlier it was 2 amperes. So 798 amperes. So that is that current. So 798 amperes. I think we missed something. Why did I write 794? It should be 798, I guess. Okay, just check that out. Yep, it was 2 amperes, right? Yeah. Is that clear, everyone? Yeah. So in NCERT, what happens is sometimes they define some new term in a in-text question, like this magnetizing current. Earlier, they have not given anywhere. Suddenly, through the question, they have defined what magnetizing current is. Don't have to sit and by heart this formula, but just remember that what it means. It means to produce the same field, how much current will you pass without any material inside. That extra current is called as magnetizing current. Okay? Is that clear, everyone, till this point? Great. All right. So that was this. Now there are different properties of material and how they behave, etc. I will explain this to you in a very simple way. And in fact, they have discussed this right over here only. Somewhere here. Where did it go? Yeah, here. What is the meaning of paramagnetic, diamagnetic and ferromagnetic? Okay, so we are coming to that now. So what is the meaning of dia, para and ferro? So these 3 paragraphs are purely theoretical. So we have to go through this. So let's understand what do they exactly mean. Okay, now just imagine, all right, something like probably Pandus. This example I often give. A Pandu is like an atom. If his eyes are open, then whichever direction he looks is the direction of the magnetic moment. If Pandu closes his eyes are closed, if eyes are basically closed, then there is no magnetic moment. The magnetic moment is basically 0. Okay, the magnetic moment is a big fat 0. If he's seeing somewhere, that's where the magnetic moment is. If he's closed his eyes, just think as if the magnetic moment is 0. If there is magnetic moment, think as if there is a North Pole here and there is a South Pole here. If he looks there, North Pole is there, South Pole is here. Imagine a classroom with many such Pandus. This classroom is like your material. What is this classroom? This is like your material. Okay. Imagine a teacher comes into this classroom. Champa teacher comes into this classroom. This Champa teacher is like your external field. If Champa is inside the classroom, there is external field. If Champa teacher is outside the classroom, there is no external field. Is this analogy clear? I will explain now all the three materials using this particular analogy. So let's talk about the first material, diamagnetic, then we'll go to para, and then let's go to ferromagnetic. When you talk about diamagnetic material, what happens is, in that particular classroom, all Pandus, just imagine all Pandus are sleeping. And our Champa teacher is right now outside in the staff room. Our Champa teacher is outside in the classroom, which means external field is 0. All Pandus inside the classroom are sleeping. That means the magnetic moment is 0. That means the magnetic field which is there of the material, or basically the B induced, that is also 0. Are you able to understand? Because all of them are sleeping. They don't have north-south polarity. That means each and every atom has no magnetic moment. Each and every atom has no magnetic moment. Now what happens? Now what happens? Basically, the teacher enters the classroom. Basically, the teacher enters the classroom right over here. What do these pandus do? These pandus, they basically look away from the teacher. That is very, very crazy. Such a disrespect. These pandus look away from the teacher. So, the magnetic moment is opposite to where the teacher's influence should be. So, the teacher is asking, listen, I am creating a field like this. This is how the external field is, but the induced field is basically opposite to it. So, because of which the net field will be basically external field minus our induced field. It will be slightly less. It's as if they are repelled by the teacher, as if they don't like the teacher. The moment the teacher again goes out, the teacher got angry, again what do all the pandus do? They again go back to sleep. They again go back to sleep. The moment teacher comes, oh, teacher is here, we'll look away. The moment teacher goes, okay, let's sleep. Teacher has come here, okay, we'll look away here. Okay, teacher has gone, okay, we'll sleep. Oh, the teacher has come there, we will look here. So that is what they are doing. Such a behavior is called as a diamagnetic behavior. Diamagnetic behavior. What will the teacher say? Go die. So that's why diamagnetic. The teacher will say, go die. So that's why diamagnetic behavior. Is this clear? So diamagnetic materials repel. Diamagnetic materials repel from the external field. If you ask me the permeability of that medium, the permeability of the medium will be less than mu naught, and the susceptibility is basically a small negative number. If you are wondering how does this come, well, look at this. Look at this. In fact, I can also put this. Relative permeability is less than 1 and susceptibility is a small negative number. How did I get that? Remember, relative permeability is 1 plus susceptibility. Because the field will become less, it is less permeable. It does not allow the field lines. So that's why relative permeability comes out to be less than 1. And if this is less than 1, that means this should be negative number. Think about it. If this is like 0.9, so this will be 1 plus negative 0.1. So that's why susceptibility is a small negative number. Got it? Clear? Okay, awesome. So that is basically diamagnetism. They have explained the same thing what I told you in a very, very boring way so that you will sleep, you will only become diamagnetic. Okay, but I have explained it to you. Same thing. Simplest explanation for diamagnetism as follows. Electrons in the atom are orbiting around the nucleus, possess orbital angular momentum. These orbiting electrons are equivalent to current carrying loop and possess orbital magnetic moment. Diamagnetic substances are the ones which result magnetic moment is there in the atom and it is zero. When the magnetic field is applied, those electrons having orbital magnetic moment in the same direction slow down and those in the opposite direction speed up. This happens due to induced current. It looks very scary, guys. It's not needed. All this not needed. Waste of time. Just remember what is happening. Okay. Now let's go to para. Everybody wants to become para now. Shall we go to the next classroom? Everybody wants to go to the para classroom. So what is happening in the para classroom? In the para classroom, each Pandu is looking somewhere or the other, lost. It's like one mental classroom only. One Pandu is looking, daydreaming. Another Pandu is looking here. Another Champa is looking at another Pandu. That Pandu is looking at another Champa. That Champa is looking at some other Pandu. Another Champa is looking somewhere here. Another Pandu is looking down here. Random. If you look at that classroom, you'll be like, what is this? Everybody is looking everywhere. So, there are magnetic moments, but if you count the total magnetic moment of that material, it will be 0. The vector sum obviously will be, will be 0 as such. And this is when our teacher, Champa teacher, is outside. That means the external influence is not even there. Now the teacher enters inside that classroom, demands that influence. She says, listen, I have come inside the classroom. So there is an external field here. These Pandus immediately, and Champas, they align themselves in the direction of that particular teacher. Earlier, each one to their own. They were looking randomly. It was completely random. The moment teacher came, they aligned themselves in the direction of the teacher. So the magnetic moment induced is in the same direction. So what will you say about the net field? The net field will be just the addition of the induced field to the external field. They get attracted by the teacher. Teacher is very nice, very charming. So they are looking at the teacher. Okay, they are influenced by the teacher. The moment the teacher goes out again they will start looking here and there. Teacher comes in, they look. Teacher comes there, they all align like this. Teacher goes out, they look randomly. Teacher comes there, they all look here. Teacher goes out, again look randomly. Teacher comes there, again they look here. Getting my point? That is the behavior. So it exhibits temporary behavior. This is your paramagnetic. What will the teacher say? Teacher will say, such para students. In Hindi, they say pyara means very lovely. So the teacher says, such pyara students. Such pyara students, that's why paramagnetic. That's why paramagnetic. Got it? Everyone? Clear? In this case, the relative permeability more than 1, because it will be influenced in the direction where the teacher is. It is supporting the teacher, so helps, attracts, so permeability is slightly higher. That means the susceptibility is definitely a small positive number. It is a small positive number, definitely. Example of this, remember, relative permeability is 1 plus susceptibility. Imagine this is like 1.2. So this will be 1 plus 0.2. So susceptibility is like 0.2, which means it is paramagnetic. Extremely clear. Very good. So that is exactly what has been explained here, and they have also given which are paramagnetic materials. Then we come to ferromagnetic materials. Let's go to ferro classroom. Let's go to ferro classroom, guys. What is happening in this ferro classroom? What is happening in this ferro classroom? Let's see. In the ferro classroom, first the teacher is outside. So external field 0. Here the teacher, Champa teacher. Oops, what happened to Champa's hair? Okay. So the teacher is inside. She demands attention in this direction. So this is the direction of our external field. It is there. Here it is not there. In this case, what happens is, in that classroom, there is a weird behavior called as a domain behavior. Domain is like a group. A group of 5-6 students will be looking here. Another group of some 7-8 students are looking here. Another group of 2-3 students are looking here. Another group of maybe 10 students is probably looking here. Okay. Another group is probably looking here. Another group is probably looking like this. It's scary. Just imagine, guys, if you ever go to some classroom like this, imagine 5-6 students looking here like this. Mental people only. Another group looking here like this. Some 7-8 students. Another group of students, some 7-8 students are looking like this. Be like, sir, I think I came to a wrong hospital or something. It is not a school, sir. I think it is some mental asylum only. Look at these kids, sir. They have formed groups and they are looking like weird fellows. They are completely dope students, sir. What has happened to them, sir? Something is wrong. They are just staring at some wall or some ceiling. something has gone wrong. Mental students only, sir. So this is basically domain behavior, guys. So each domain looks in one particular direction. The magnetic moments. This is another domain. 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 Another domain. Now what happens when the teacher, Champa teacher, Pavam teacher only, imagine she has to go and teach to such a classroom. What will happen? Gone only. So this Pavam teacher goes inside that classroom. What happens is all the groups which had magnetic moments in that direction, like this group, this will start growing in the size. They will start growing in size. That means they will conquer other group members. This guy will say to this guy, hey, listen, why are you looking there? Teacher has come there, come join my group. So they will expand their group. The domains will basically expand. This guy will say, okay, I'm also looking at the teacher. Hey, listen, you three people, what are you guys doing? Come on, let's look at the teacher. Let's look at the teacher. These people might also, some of them might join, some of them might not join. But, you know, more or less you will see the groups will begin to expand. Groups will begin to expand in the direction of the magnetic moment. That is what you will see. Because of which the net magnetic moment which is induced is in the same direction. Is in the same direction as the external field. And what you will see, this net magnetic field is definitely the sum of our external field and our induced field. But this is much, much higher. This is much, much higher than the paramagnetic case. And the best part is, if the teacher leaves the classroom, what do you think they will do? Will they come back to their original groups? Remember, this guy had said to this guy, listen, don't look there. Teacher has come, look here. So they started looking there. When the teacher leaves, what will they do? They won't change. If the teacher came, one group member who was looking here, started looking here, that's it. They have joined the group, guys. They will not change. So they assume permanent magnetic properties. So that is why ferromagnetic materials, are used to make permanent magnets, full mental only. Imagine these group members got conquered. Now everybody is looking here. Everybody is looking here. It will be scary, guys. Got it? Clear? So it exhibits permanent behavior. Permanent behavior, even if the teacher leaves. Such cases, susceptibility and relative permeability. Well, relative permeability, of course, is much, much larger than 1. Susceptibility is much, much larger than 0. Like 200, 500, that is how the order is. Is that clear? So that is exactly what is explained here. Domain. See, such boring things. Such boring things. Okay, they have mentioned here. Who are ferromagnetic, etc. is mentioned here. After this explanation, read this theory. Trust me, you will never ever find this difficult. I hope I gave an amazing explanation. That's the end of the chapter, guys. If you loved this explanation, put it up in the chat box. Put it up in the chat box, okay? So, which kind of classroom are you guys going to be? Are you going to be dia, para or ferro? I want to see it in the comment section, okay? So, if you are something else, then please write it, what kind of classroom you guys are. And some of you will be like, sir, we are in YouTube classroom, sir. Sir, the moment you come, sir, we look at you. The moment you are not there, sir, no motivation only, sir, we keep sleeping. So, sir, we are paramagnetic in nature. Okay, I hope you are paramagnetic, but I feel over the course, you should become ferromagnetic. Even if the teacher goes, you should still be staring at the screen. Yeah? Okay. I mean, not literally. That means you should still be studying. Just because I am there, you should not be studying. Even when I'm not there, you should still be studying. So hopefully you become ferromagnetic. All right. Bye-bye. Have a great lunch. Take care. Hasta la vista. Captain Shreyas signing off.